yesterday we basically finished the first part of chapter 1. Okay, so one of the key points of yesterday's lecture was the discussion on complex exponential signals, and in particular we spent a lot of time discussing this complex exponential with a pure imaginary exponent. Okay, so this is in continuous time, which by Euler's relation you can write as cosine omega naught t plus j sine omega naught t. Okay, so the reason we spent a lot of time talking about this is because this is going to be one of the most important basic ingredients of this class. Okay, so this complex sinusoid is considered as a pure frequency component, right? A frequency that contains purely, a signal that contains purely the frequency omega naught. Okay? Now, later on, we will show through Fourier analysis that a large class of signals, right, almost all signals that we may encounter in practice can be written as combinations of these signals. Okay? So this helps us understand what are the underlying frequency components of the different time domain signals that we're looking at. Okay? So one takeaway message of this course is that most practical signals that we will deal with can be written as linear combinations of these pure frequency components. Okay? These pure sinusoidal signals. All right, so this is what we will talk about in later chapters. All right. So today we continue with some basic signals that we will use in our discussions. So the next one is the class of unit impulse and unit step functions. Okay. So for this, we start from the discrete time case. Now, a discrete time unit impulse function or a unit sample is denoted by this delta of n, which takes on the value 1 at time 0 and 0 everywhere else. Okay? So a unit impulse function looks something like this. You have only the sample 1 at time 0 and 0 everywhere else. Okay? Now, what's closely related with this unit impulse function is the unit step function, or sometimes called unit step sequence in discrete time. So what this unit step sequence is right, this u of n that is equal to 1 for all n greater or equal to 0 and 0 everywhere else, right? Basically in the negative domain. Okay? So if you plot this out, right, the unit step sequence takes on the value 1 for all n greater or equal to 0 and 0 everywhere else. Okay. So these two functions are closely related because you can express one using the other. Okay? So first of all, if you look at the unit impulse, delta n, okay, you can see that this is equal to u of n minus u of n minus 1. Okay? Because u of n is this, and u of n minus 1 is this signal shifted by 1. Okay? So if you subtract u of n with u of n minus 1, what's left is only the sample at time 0, which gives you delta n. Okay? Now you can also express u of n, the unit step sequence, using the unit impulse functions. All right. So in particular, one way to write this is to write it as the summation of delta n for delta m for m from minus infinity up to n. Okay? So we're basically summing this function from minus infinity all the way up to time n. So this is sometimes called the running sum of the function. Okay? So if you look at, if you try to, visualize this operation on the figure up here, what you're doing is that you're essentially summing all points of this function, right, all the way up to time n, let's say, is here. Okay? So you're summing over all these samples up to time n. Okay? So if n is less than 0, then you're summing a bunch of zeros, which is still 0, right? But if n is greater or equal to 0, then you're summing over a region that has this one sample and 0 everywhere else, which will give you a sum of 1. Okay? So for n less than 0, you're summing all zeros. That's why you get the 0. And for n greater or equal to 0, you're summing over one of these pulses, and therefore the sum is 1. Okay? So this is one way to write the unit step in terms of the unit impulse. Okay. Now, by a change of variable, suppose we set k equal to m minus m. Okay? In that case, we would be summing k. Okay? So originally, right, I'm summing m from minus infinity to n. Okay? Now, if I do a change of variable, substituting m with k that is equal to m minus m, okay, then minus infinity, right, substituted here becomes infinity, and m equal to n substituted here becomes k equal to 0. Okay? So you're now summing over k from 0 up to infinity. Okay? Of delta m, right, m now becomes, right, if you move this over here, m now becomes m minus k. So I have delta of n minus k. Okay? Now, if you think about it, what is this function here? Okay. So this function is the delta function, the delta impulse function, shifted to time k. Okay? So originally, the 1 is at time 0, but when you shift by k, the 1 now appears at time k. Okay? So what you have is a function like this. So at time k, you observe this impulse of 1 and 0 everywhere else. Okay? So this is delta of n shifted to time k. Okay. So when k is 0, this is a delta function here, right? When k is 1, right? When k is 1, you have a delta function here. Okay, when k is 2, you have an impulse here, here, and so on and so forth. Okay? So this is like, the superposition, right? This is saying that the unit step sequence is like the superposition of these individual time-shifted impulses. Okay? So this is another way to write the unit step in terms of the unit impulse. And intuitively, this is viewed as the superposition of time-shifted impulses, okay, that constitute this step function. Okay. All right. Now, the unit impulse is also often used to represent the sampling process. Okay, it's also often used to represent the sampling process. Okay, so for example, suppose we have a discrete time signal like this. Yorma. Oh, okay. Okay. So suppose that you want to sample this function at time n naught. Okay. Then what you're effectively doing is multiplying xn with a delta function at time n naught. Okay, and 0 everywhere else. Okay? Okay. So if you multiply this with this, what you're left with is this sample here. Okay? So one application of a delta of this unit impulse is to represent sampling at time, or sampling of the function at time n naught. Okay? And like we just mentioned here, you can represent this as xn times delta of m minus n naught. Okay? And when you multiply xn with this delta function at time n naught, the only non-zero value you would observe is this value at time n naught. Okay? So it's equivalent to write this as the value of x at time n naught times this delta function. Okay? So multiplying the function by this unit impulse at time n naught sort of extracts the value of xn at that time. Okay? So this is exactly what we do with sampling. Now, we're tempted to define the same operations or same signals in continuous time as well.